Okay, brother. Now we are starting a new module that is about design of steel structure according to Eurocode. So, are you listening me?
Yes, I am.
Okay. So I think this is a general introduction of steel structure. So the first slide is just about the steel grade. Okay. Steel grade mean that what is the yield strength of steel. Okay, so according to Eurocode there are actually four different standards of steel. The first one is 235, 275, 355 and 450 steel grade. Okay, but as this grade shows that the yield strength of steel is 235. Okay, but it Noman, I think your voice is disturbing us. Noman, your voice is disturbing us. Okay, so must remember that this is the Fy mean that what is the yield strength of steel. Okay, and Fu mean that the ultimate strength of steel. Yield strength mean that in what strength the steel start the steel structure start yielding, and Fu mean that what is the ultimate strength of steel. Okay, for example, if I just want to show you through a graph like that, this is your stress and this is your strain. Okay, when force is applied on steel structure element. Okay, one thing should be remind that this is a structural steel. Okay, structural steel has a different properties as compared to reinforcing steel. Okay, reinforcement steel like this is bar, but this is a structural steel. Okay, so the behavior of structural steel is slightly different as compared to reinforcing steel. Okay, so when you apply a stress on structural steel, it will show the behavior like this. Okay, like elastoplastic. Okay, elastoplastic mean that in some extent it remain in elastic and after that it come on a plastic range. Okay, this is your elastic range and this is your plastic range also. Okay, so this is your fy and this is your fu. So fy mean that at some point you are not increasing the load. Okay, strain, but there is a strain on structural steel. Okay, so if your grade shows that your yield strength is 235 and your ultimate strength is 360, but it depends on your thickness of flange. Okay, this is thickness, but it shows a thickness of flange. Okay, for example, if you have a section like that, okay, T section. Oh, and your thickness of flange is equal to 9.5 mm. Okay, so now your thickness is less than 40 mm. So in this case your yield strength is 235 and your ultimate strength is 360. But if the case is like that, if your strength is uh, if your thickness of flange is greater than 16 mm, or 16 mm. One thing I want to show that, one thing I want to share here that this graph is not throughout and not detailed. Okay, this range, if there are, you can say that there are different ranges. For example, the first range is that if your thickness of flange is greater than 16 mm, if and less than 40 mm. The second option is that your thickness of flange is greater than 40 mm and less than 80 mm. Okay, so I think there is a lack of one column here. Okay, but for this you just need to understand that your yield strength and your ultimate strength of your structure steel grade, it depends on thickness of flange. Okay, so for example, I just want to give you an example. For example, you are solving any numerical and here it shows that your thickness of flange is 42 mm. So what is the yield strength of 235. So you just need to go 235 and you see that the thickness of flange in which section your thickness of flange lies, you just need to pick this value. Okay, so similarly this is according to Eurocode. These are standard. Okay, so but we are follow this standard Eurocode. This standard, this is I think latest standard. Okay, now steel structure elements, steel structures. Okay, so according to you can say in universal in UK, or you can say in British standard, or in Eurocode standard, there are different type of steel structure sections available. Okay, the first one is IPE sections and the second one is UB or UC sections. Okay, so there is no much difference between them, it is just the names. Okay, for example, he says that this is the IPE profile like a 3 mm 300. For example, if you have a structural drawing and it shows that this is equal to IPE 300, so you just need to go to IPE profile and see that what is the height of section. Okay, what is the breadth, what is the thickness of flange, and this is thickness of up, and this is r, this is like a radius of fillet. Okay, and this is the area of section, and you have all of the properties here. Okay, so this is the section properties. Now we are going to simple geometrical properties. Okay, so you know that this is a very basic formula of moment of inertia, and which is BD cube divided by 12. Okay, and this is a section modulus. Okay, so section modulus is actually you can say that the derivation of section modulus is like moment of inertia divided by height over 2. Okay, so the moment of inertia is BD cube divided by 12 and height over 2. Okay, d over 2. Okay, so in this way 2 6 and d BD cube and scale. Okay, so this is BD over 6. Okay, so this is a section modulus. Okay, so the section modulus formula, he doesn't mention the section modulus formula is, you can say section modulus formula is I over h over 2. Okay, so one thing again I want to show here that it is a elastic section modulus. Okay, there are two types of modulus. The first one is elastic section modulus and the second one is plastic section modulus. So what is the difference between, here is the difference. Okay, for example, this is your graph. Okay, and here is the graph. It shows like that when you apply a stress on steel, for example, this is your steel section. Okay, for example, your steel section, this is a plate, this is B, your D. Okay, so when you apply a stresses, it you know that the stresses is like that. Okay, stresses is like that. For example, if I show you in a longitudinal section, it will show like that. This is your elastic elastic stresses. Okay, so as far as you increase the load, you can say that your stresses will be like that. Okay, your stresses will be like that. So this is your elastic stresses and elastic section modulus, and this is your plastic stresses and this is your plastic section modulus. So plastic section modulus value is always greater than your elastic section modulus. So in simple, if I say that what is the elastic stresses and what is the plastic stresses, is simply if you apply a load on any structural steel, you see that the steel start bend. Okay, so as you increase the load, you can see that there is a plastic hinges occur on in this section. Plastic hinges mean that the section starts cracking. Okay, so cracking is, you can say that is associated with plastic section modulus, and before the cracking occur, it you can say that it is associated with elastic section elastic stresses. Okay, The formula of elastic section modulus is elastic section modulus. The formula is moment of inertia and h over 2. H over 2 mean that total height divided by 2. Okay, and this is formula for elastic section modulus, but for the plastic section modulus you need to calculate everything by your own. Okay, but if you see the section properties, so everything is available. You don't need to calculate everything by your own. Okay, so again, this is your IPE profile. So whenever you in ETAP, uh, for example, uh, one thing, remember that in IPE profile or in any UB or UC profiles, everything is based, already is based. It is already constructed. Okay, so it is, you can say that it is already built in section. Okay, but if you want to make your own section, for example, you want to make your section like b is equal to 178 mm, it is equal to 7.8 mm, and like that. So you just need to draw your cross section on etab and go to the section properties, so it will show all the properties. Okay, so it is shows, it is the etab analysis. And again, this is IP profile, and this is what I'm trying to say, that is elastic section modulus, and this is plastic section modulus, and this is your elastic section modulus, this is your plastic section modulus. Okay, there are two axes. Okay, so if there is x-axis or the y-axis, so you have a both axes, but here this is showed is a z-axis. Okay, so again, in some of the time, in some time, you have other type of section profiles like HE profiles. Okay, so there is no difference, difference between IPE profile or HE profile. You can use any of them. Okay, so it depends on your question, that either which kind of profile does your professor ask or you want to use, so you can use any of them. Okay, so again, it is which is a ETAB analysis, and it shows that how can the section properties can be achieved. Again, this is a HE profile, so there is no as difference. So do you understand?
Yes, I do.
Hello? Okay. Just give me a minute.
Sure.
Now it shows some of the properties of either the section, how can a section you can say behaves. Okay, so in this slide there are mainly two types of sections it will shows. The first one is, you can say, a column behavior, and the section one is beam or flexure. Okay, as I explained you in previous slides about what is flexure. Okay, where there's a prominent of bending and shear. Okay, so you see that in axial forces. Okay, the formula is like NRD, or you can say NRD or NED. NED is mean that the ultimate axial strength, stress, and A is the area of cross section, and FYD is actually the design design yield stress of steel section. Okay, and this is the bending resistance formula. Okay, MRD is equal to FYD and
So
WY.
the NED and the NRD are the same?
Yes, you can say, because in most of the Eurocode they use NED, but NRD is, you can say, it is same. There's no as such difference.
Okay.
Okay, so these are some of the you can say little bit advanced advanced top, it's not advanced topics, but you can say there's advanced related to these formulas. Okay, So but for now you just need to consider, you just need to know that this is the formula to design any axial member, and this is the formula to design any flexure member. For example, if you want to design a beam, you can use this formula, and if you want to design column or any truss element, so you can use this formula. But this is not you can say that this is not I don't say it's a correct, but it has some limitations. For example, this is either is a plastic section modulus, is elastic section modulus. Okay, so when next slides come we can see that. Okay, so this is again what I'm trying to say, that there is a difference between a behavior of any cross sections. For example, this is a behavior of RC beam, okay, and this is the behavior of steel beam. Okay, so you know that RC beam is a composite structure. Composite mean that it has a steel plus concrete. So you can say that the RC behavior is as little bit complex behavior, but steel is only made up of steel element, so it is a homogeneous, it has no different composition. So the behavior of steel beam is not as complex as compared to steel. Okay, so for example, if we see that this is a your beam, RC beam, okay, and it has a steel on bottom, which is named as tensile reinforcement. So just want to change the color. So you know that, for example, this is a neutral axis, and you know that the concrete below the neutral axis is under the tension, and the concrete that is above to your neutral axis is considered as a compression member. So what you need to what we assume that in RC structure, we assume that and the concrete under below the neutral axis is failed, and the only concrete that is above to your neutral axis is considered. Okay, so the behavior is like that. Okay, so this is your compression stresses, and 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 this is your TS. Okay, this is your AS mean that what is TS TC means that tense, you send compressive stresses of concrete and tensile stresses in steel. Okay, so but for this you can say for this course, you need to understand this behavior. Okay, so what is this behavior? This behavior is considered that this is your elastic stresses, which I have explained you earlier, that when you start loading on any steel member, it behave like that. Okay, their fibers behave like that. Okay, but as long as you increase the loading, okay, as long, this is what I'm trying to say, this, okay, this is your yield point. So this is your elastic section. Okay, this is your elastic section, and your stresses will be like a triangular. But as long as you achieve this limit, like yield limit, the section start yielding, and your stresses will be rectangular stresses. Okay, and for this section, the section remain in elastic, and elastic section of modulus is achieved, and for this is a plastic section. Okay, so now come to another topic, that is about local buckling. Okay, so local buckling is characterized by local deformation of slender cross section element by on rotation and nodes. For example, sometime it happen like that, there is a member that is so slender. Okay, slender mean that it is very long. Okay, simply for example, if I give you a simple example, if there is a rod like that, for example, this is a rod. Okay, So I don't think so it will be buckle. But if this is a rod and it will be like that, okay, and we don't apply any kind of load, it will be little bit bent by its own weight. Okay, so this is called local buckling. Okay, local buckling is just that due to its slenderness, it means that due to, now the question is that what is mean by slenderness. Slenderness mean that for example, if I'm talking about, like for example, if this is, just remember that this is a cross section, and you observe that I just draw the thickness of flange is very less. I'm not going to a detailed engineering analysis or engineering formula, but you maybe consider that this thickness is so small, and maybe before applying the load, it will be bent. But if this is your, for example, if this is your section, so you say that maybe this thickness of flange is better as compared to this. Okay, so this is what I'm trying to say, that this is slenderness. So whenever you have designed any structure, you have to consider slenderness. So what is the slenderness? It is always it is always a ratio between this to this. For example, what is the breadth of thickness of flange ratio and what is the height to thickness of web ratio. Okay, so this is what I'm trying to say. Okay, so this is your slenderness. So it depends on the slenderness aspect, which is width to thickness ratio, the type of load, distribution of compressive stresses. It also depends on where you actually applied a load. For example, for example, you have this type of section and you apply a load from here, so maybe only this and this, this, if you can say that flanges affect. Okay, but if you are applying a load in axial, so it also, this section affects. Okay, so the slenderness also depends on the type of element that are used. For example, if you are using, if you are designing a you are designing a flexion member, the slender aspect is different. Okay, and if you are designing a compression member like a column, the slenderness values are different. Okay, because the loading is different, and the type, you can say the each, for example, this is, we have three elements here, one element, two element, and three element. For example, if we apply a loading in a beam, so it, this section, these sections, you can say that are affected. But if we apply a load on like axial, so maybe this section is affected. So you can say that slenderness values is can be changed for beam and for column. Okay, so now again, according to Eurocode, this is what I'm trying to say in the whole lectures. Okay, now I hope so you can understand it better here. Okay, so now, for example, you have this type of section, I section, and you are applied a loading. Okay, and your stresses is less than your yield. For example, this is your, and this is your graph. Okay, and again I draw a graph like here. For example, you are applied a load and the loading is just like Fy, and your stresses is less than your Fy. Okay, so this case is achieved, and according to Eurocode, you can call the section is class 4. Okay, and as soon as your Fy, you can say that as soon as your stresses reach to your Fy. Okay, this is the case. Okay, so that the stresses on the top of the section here, it increases. Okay, you can see that it is increases. Okay, so now the section is called section 3. Okay, and as soon as this value greater than your Fy, so you can say that your section is either section 1 or section 2. Okay, so you can call either the section is section 1 or section 2. So this has a maximum strength, okay, this has less strength, and this has to less strength. Why? Because the stresses is not uh, go to far beyond. Okay, so this section is more as a more strength as compared to this and this. Okay, this is again what is shown here. Okay, like that. And again, m is the moment of resistance. So again, in this section, your elastic section modulus is achieved here. Again, elastic section, and here this is a plastic section. So you can say that this strength is elastic strength, this is again elastic strength, and this is your plastic strength. Okay, again this is your plastic strength, plastic strength, elastic strength, elastic strength. So in short, say that this is your elastic strength, this is your elastic strength, this is your plastic strength, and this is your plastic strength. Okay, so this is what I have explained you in all. So you can say in theory. Okay, so in short, I say that the most important, I just want to show that in class 1 plastic hinges will occur. Why the plastic hinges is occur? Because I told you, if you apply a load, it remain in elastic, but as long as you apply a load, the hinges is occur. So what is hinge mean? You can say in simple terms, you can say hinges a crack, or a point where the section reduce its all of the strength. Okay, so the most important thing is that in class 1 plastic hinges achieve. Here there is no plastic hinge, no plastic hinge. Okay, so this is all the theory. If you want to study, you can study, but I have explained you. And this is a local buckling. Okay, so this is again elastic section, elastic, and this is your plastic. Okay, so this is what I'm trying to say, that in this, if you want to if you want to find the strength, you will use elastic section modulus. Again, if you want to find the strength of this section, you are using elastic section modulus. And for this, if you are designing, you have to use plastic section modulus. This is what it explained. In class 1 and 2 you are using plastic section modulus, and for class 3 you are using elastic section modulus. So this is a just simple example. For example, you have a steel grade of S275, and this you have a IP profile of 300. So class 1 and class 2 section, so you just need to pick two values. The first one is plastic, and you need to select elastic. So you just go to IP profile and select this value and this value. Okay, and you just need to multiply it by 275, so it will be your moment value. This is your yielding moment, and this is your plastic moment. So this is again local buckling. Okay, now just give me now now you have to find the exact way to find the section classification according to your code. Okay, so I think there is some example here, and I want to show you through detailed calculation. Yes, this is the calculation. Okay, so what you need to do is just I want to show you in here. First of all, for example, you have a steel section. Okay, and you have this B, this D, this D, and this H, and this R, radius of fillet. And you have a grade strength of, and you have the steel grade like 275 and 235. Okay, so what you need to do is you first need to find E value. Okay, this value. Step 1, E, which is equal to 235 by Fy. So my question is that what is Fy? Fy is depend on the grade of steel, for example. And again, it is not only depend on the grade of steel, it is also depend on your Fy, or your thickness of flange. Okay, so for example, it in question it says that your grade of steel is 275 and your thickness of flange is 13 mm. As your thickness of flange is less than 13 mm, so your strength is your yield strength is 275. But if says that your thickness of flange is 18 mm and it is exceed to 16 mm, so this is equal to 265. Okay, so what you need to do is 235 into 265 under root, you have some value. For example you have this value. So first step is to find E. Okay, this is the first step. Second step is you need to find flange aspect. For example, I'm not following this you can say, yes, we can use this. Okay, it is better to follow this example. Okay, so this is your breadth, height, d is this distance. Okay, thickness of flange, thickness of web, r. Okay, so now it is written that the thickness of flange is 17 mm. Okay, and again, according to most of the Eurocode, latest Eurocode, this is not 275, this is 65. I will show you at the end of this lecture. This is 275, 265 because it is exceed to 16 mm, but your professor is not following these notes, so you can use 275. Okay, but most of the Eurocode it is 265. But now we are following this lectures, so 265 and this is equal to 0.924. Okay, so this is your E value. Now you have to check the flange. Okay, flange mean that what is the, for example, what is the what is the ratio of this length to this length. Okay, so how can you find this length? You simply divide your I will show you in simple way like that. He will show 154.4 minus, okay, minus thickness of web, which is thickness of web 9.6, minus 2r divided by 2 thickness of flange. Okay, 17. So in this way your value comes 3.66. Okay, now according to Eurocode, okay, according to Eurocode, the limit for class 1 section is equal to 9e, 9 iota, you can whatever you call. Okay, 9e. So when you multiply by 9 with this one, your value come at 8.34. It means that your actual value is 3.66 and the limiting value is 8.32. It means that your section is under this limiting value. It means that your section is class 1. Okay, now come to a point of web. Okay, so the web formula is just, you need to find just the height, this is your d, and thickness of web. So your height is 462. Okay, this is the formula, height minus 2r. So height is equal to 462 minus 2, r is 10.2. So it will be 476.407.6 divided by thickness of web. Okay, so it is 42.46. Okay, now according to Eurocode, your limiting value for class 1 section is equal to 72. Okay, so the 72 equal to 66.53. Again, your value is under this, is less than this value, so your web is also 1. It means that your whole section under your whole section is class 1, and when you are finding the strength of this section, you will use plastic section modulus. Okay, you don't need to pick plastic section modulus, you need to pick plastic section modulus. Okay, so again, this is this is the whole limits. Okay, okay, now for from this up to this question. Okay, this limit is this limit 9e and 7e, this is for beams and for flexion members. Okay, but if your section is subjected under a compression, okay, compression mean column, for flange it is equal to 9e. Okay, but for web the limit is 33, 38, 42. Okay, but for beam your flange limit is equal to 9e. Okay, for class 1, but for web in compression there is 33, 38, 72. Okay, so these are the some limiting values. Okay, so I will just give you from also give you from example from like that. You can, this is you can study from here. Okay, 72, 33, 83, these are the bending. Okay, for example, if your value is less than 72e, it is class 1, but if it increase to 72 and less than 83, so your section is class 2. Okay, so these are again limiting values. Okay, these values are for compression, for bending. Okay, and these values are for compression. And maybe I have some notes in which these values are written more clearly. You don't need to study all these values by your own in table. I have some sort of table which has it is clearly written that what is the value of limiting values for class 1, class 2, for bending and for flexion separately. So I think this is the end of the lecture. So if you have any question, you can ask.
Thanks a lot. But I asked Mr. Naman already. But if you could, just send me the names of the letter, like the description of
Yes,
what the FCK.
yes,
Because as you see
I
now, slides are pretty stupid. Like he's missing a lot of stuff from the slides.
okay, I'm sorry for being late. Actually, I was going to
No,
somewhere.
it's
Let me
alright.
show.
And
I write here. Okay, and what you want? Should I write here, and should I write it separately?
you can write it separately. You can take your time. Maybe by the end of today or tomorrow morning is
No, no.
fine.
For example, I will just write here, and I will send these slides of to you. Okay. So FCK is a compressive strength, compressive characteristic strength. Okay, characteristics strength of concrete. Okay, and FYK. FYK is yield. K mean characteristics, strength of steel. Okay, and FDY is design, yield, strength of steel, and AS mean the area of steel. Okay, if it is written as T, it means that area of tension steel, and if it is written as ASC, it meant that the area of compression steel.
Okay. FCD.
Where FCD?
I think it
F.
was in the previous slides. I've worked with FCD. Maybe it's in the coming slides or something, but it's
Yeah,
a lot of.
it's a design. It is a design compressive strength of concrete. Okay,
Okay.
actually, you can say that characteristic strength is always greater than design strength. For example, I say that the characteristic strength. What is the characteristic strength? Characteristic strength is the directly strength which we achieve from testing material. For example, I took a cube and I apply a load. It has broke. It has broken on a load of 50 megapascal. So that we say that the characteristic strength of concrete is 50, but I don't took it whole. I just say that it is 45. So this is a design strength. So design strength is a little bit less as compared to the characteristic strength.
Okay, so the design strength is basically with the safety factors in place, right?
Yes.
Okay.
But one thing I just want to explain to you that your professor are using the design strength parameters.
Uh,
Most of
okay.
the books are not using these values, design strength, because it is used in working stress method. But I don't know why your professor using a limit state method, because if you study Eurocode book which I have mentioned, that Eurocode 2 is about mostly you did not see this parameter while designing of concrete. But this is not, you can say it is not a big difference. You can use any of them, because there is not a difference. For example, the characteristic strength of steel is 500, and the design strength is 435. So it doesn't make a big difference.
Okay, yeah, understood. But Mr. Fahad, I'd really appreciate if you can, and maybe in a Word document, if you could type what's MRD and what's WELY, and I know it's plastic and elastic, but during the exam time, just to revise, I
Okay,
should like what exactly I'm calculating. Makes it a lot
okay,
easier.
okay, okay. You can just text me or text Mr. Numan for what you want to learn. I will type you in separately. Okay.
Okay, yeah, that's fine. No worries. I appreciate
Okay,
that.
brother. Okay, brother. Thank you.
No worries. You're
I
welcome.
I hope so. I hope so. You will understand lecture as well as the theory behind these things.
Inshallah, inshallah.
Okay, okay, brother. Thank you. Allah Hafiz.
Allah Hafiz.